So let's pick up where we left off in talking about machine learning. Now we've prepared our data set. Now we're actually going to estimate a machine learning model. And more specifically, we're going to estimate a random forests model. Again, one of the most common types of machine learning. So we're going to start off actually by talking about this train-test split, which is often a first step with your data set to separate it into a training portion that you estimate the model on, and then some of the data that you hold back to test the success of your model on data it hasn't seen before. And then we're going to actually estimate and start to interpret a random forest model. Let's continue with our example of ADUs, and we can load in. We saved this as a pickle file before, so let's use the read pickle to read this file that we saved at the end of the last lecture into pandas. And it looks like what we had before. We have a column on the end that has ADU. And this is going to be a dependent variable that we want to try and predict. So in almost any prediction problem, as I mentioned, we want to split the data into a training sample and a testing sample. And this assumes you have enough data to do this. If you have several thousand observations and up, it's a good way to evaluate how well your model is doing, the predictive accuracy. And it's kind of cheating to estimate that on data that you've used to train it. So the idea is to hold back some data that the model wasn't trained on and is new to it, which is perhaps a representation of, like, if you're predicting in the future stuff that really isn't known right now, how likely is your model to be successful in that regard. The scikit-learn library, which is what we're going to be using for most of our machine learning analysis, has some built-in functions to split the data. And if you want to replicate your analysis, this random state argument can do that. If you've used statistical software that has a seed argument, this is exactly the same thing. Basically, it chooses the same quote-unquote random or quasi-random number every time, so that even though there's some randomness in the process, you're going to be able to reproduce your work. So let's look at this function, the train-test split. What does it do? So it looks like it takes some arrays of data, and then you can specify the size of either the testing data or the training data. And so what does test size do? Well, it can be a float between 0 and 1, so the proportion of how much data you're going to include in the test split, or it could be the absolute number of test samples. If you prefer, you can choose the size of the training data set instead. And again, this random state argument is controlling the randomness so you can reproduce your results. It doesn't matter what argument you pass to it as long as you pass one. So at this point, we also need to choose our variables. And our y variable is going to be whether there is an ADU or not. This is the has ADU column that we created in the previous lecture. And for our x variables, our predictors, in regression terms, these are on the right-hand side of your regression equation. Let's just start with a few that might be interesting. The square feet of the main dwelling, or the main building, the land value in the assessor's role, and the value of the improvements, so the buildings, also from the assessor's role. We're also going to need to drop some null values. In many cases, a function in pandas or NumPy does this automatically. You don't have to worry about nulls. But in scikit-learn, in machine learning, it's usually not going to do that for us. We're going to have to manually drop the null values. So let's define our list with our x variables, specify our y variables. Let's create a data frame that we're just going to fit the model on, which is going to be what's in our join data frame that we load in. And it's going to be a subset of the columns. So we're converting, this was a string, so we're going to convert this to a list, so we can create a list of 4 variables, these 3 plus the y variable. And then we'll drop the NAs before we store it in this variable. And then let's create these, so train test split returns 4 items, the x train x test, y train y test. And so we're going to pass our x variables to it, our y variable, and specify that our test size is going to float between 0 and 1. We're going to hold back a quarter of the data in order to test. So if we look at the length of these, well, the length of the x and the y should be the same, which they are. We have 583,000 or so observations in our training data set. And we have just shy of 200,000 that we're holding back in order to test. These are the lengths of these test arrays, both the independent and the dependent variables. So because we specified the random state parameter, we're going to get exactly the same sample. So let's look at the first 5 rows of xtrain. Because we have random state, let's do this again, and we are going to get exactly the same result. But if I change this, say to 2, we're going to get a different sample. So let's change this back to 1, so we know what we are doing. So now we're ready finally to do some machine learning. So let's talk conceptually a little about random forests. Now the idea of the random forests comes from the idea of decision trees. So at a really crude level, imagine a classifier that is predicting that you have an ADU that has ADU as true if your lot is residential and it's large, if it's larger than 5,000 square feet. Otherwise, it's going to be false. And we'd estimate the exact threshold, such as 5,000 square feet, from the data. Well, we can see an example of these trees from this Reed's article about urban gentrification that was on the reading for this module. So we have this tree that we walk through. And in each stage, we're looking at one of these variables at each node. So here we're looking to see if this field, higher professional occupations, is less than or equal to 2.066. And there's 25 samples at this point. If it is less, then we go to this node. And we have 16 samples on this branch of the tree, and then we have another choice. If not, we go to this branch of the tree. And so it's a hierarchical decision tree, and then we end up at these leaf nodes. So you might think, well, this is kind of deterministic. Like this, it seems hard to fathom this is going to do a great job at prediction. And you'd be absolutely right. That's why the concept of random forest comes in, which are a collection of these decision trees. So basically, we estimate lots of these individual deterministic trees. Each of these trees is going to be trained on a subsample of the data set, or a subsample of your subsample of the training data set. And then we're going to combine these predictions. So it's kind of like a wisdom of crowds approach, or wisdom of trees in this instance. And so because of that, this process is called formally ensemble learning. We have an ensemble of trees, and we're going to try and learn from the collective wisdom of them. If you want a more in-depth explanation, then this article by Neil Lieberman is a great overview of the concepts. So random forests are implemented in the scikit-learn machine learning library. And one of the important parameters is going to be this n estimators. So this is basically the number of trees that you are estimating. And up to a point, there's certainly diminishing returns, but up to a point, if you have more trees, you're going to get better predictions out of your model, but it also takes longer to estimate. And so it's a trade-off between computational time and predictive accuracy. So as a general rule, while you're experimenting, while you're trying to get your code to work, especially in terms of the syntax, just use a small number of trees and then you can scale up. Even with 50 trees, I heard my computer's fan run quite a bit faster. So this line of code just creates the classifier object. It doesn't actually do anything at that time. We have this RF object. And then this is what's doing the work. And notice it's fitting it to this training data based on the X observations and then our dependent variable, the Y observations. So this is what's taking the time, this line, and this is what's doing the work. And it seems that we end up with a random forest classifier. So what do we do now? Well, now we've estimated the model on the training data set. Let's see if we can actually have any success in predicting whether an ADU is going to be built on something it hasn't seen, something from our testing data set. So we use the predict function from this RF object. Rather than using the train, which we did up here, we're using the test. And so we're creating a vector of predicted values. And so if we look at it, we're getting, it's predicting no ADUs on each of these parcels. And let's look and make sure that the lengths are the same. We have 194,000 and so parcels in our testing data set, and we're getting the same number of predictions. So how do we assess the performance of this model? Well, we'll do a little more depth on that in the next lecture. But one really quick check is just to look at the means, the percentage of true observations. So what's the mean of this? Remember, if you're taking means of true or falses, the mean is the percentage of true values. So this is our predictions, and this is the real number in our actual holdback sample of the testing. So this really doesn't look good, right? We're predicting less than 0.1% of our parcels will have an ADU, when in the real world, more than 3% of them did. So what's going on? Well, in the next lecture, we're going to look at some more sophisticated ways to assess the predictive accuracy of the model and actually compare different models so we can do better from this. And we are going to be able to do at least somewhat better than this. But for now, let's see if our overall predictions can be improved by a few extensions. Maybe we can add some more variables. Maybe we can add more trees to our estimation, so more trees in the ensemble. We can also adjust some other hyperparameters. The number of trees is one of the hyperparameters, but you can look at some of the other options in the documentation for this random forest classifier. So before we go on, I want you to take a look at the documentation. So Google random forest classifier, see how you can increase the number of trees, but also take a look at the other hyperparameters that you might experiment with. So let's continue by throwing all the variables in our data set into our model. Now, if you've taken classes on statistics and regression, this is a really bad thing, right? This is a kitchen sink regression model with no theory. That is a really bad thing to do in most circumstances. But in our predictive framework of machine learning, we can actually throw in the kitchen sink, and we can rely on the random forest or the other machine learning model to separate out what is useful and what isn't useful. One wrinkle here is that string variables need to be encoded into what's called dummy variables, which are 1 or 0, before we can use them. So for example, if we look at our use type column, we have residential, commercial, recreational. Python machine learning functions are not going to be able to make use of these directly. So let's convert these into a string, a series of columns, using the very helpful getDummies function, which converts these types of categorical variables into dummy or indicator variables. You can see it takes some data, and then there's some optional arguments, such as like what we want these columns to be called. We have the same for use description. This is another field in our parcels, and so this is a more fine-grained version of the use type. Everything from refrigeration and paint shops to golf courses to apartment buildings. So let's use getDummies. We're going to pass the use type, create dummies from this, and then we're going to prefix this column with use type. And we'll see what this looks like in a moment. And then we're going to do the same for the use description. We're going to put it in a data frame called dummies2. And then let's look just and see what it gives us. So this is our original data. They're all residential. And we can see that our dummies, they have 0 for use type commercial, because none of these are commercial. But if we look over at residential, we see all of these have a 1 value for residential, because that value is in the string column is residential. So it creates this single string column and creates 8 or so columns that are 1s and 0s that we can use in machine learning. And notice that this index here is the same as our original data frame. It's the APN, so we can join these back. So that's to our join data frame. Let's add dummies1, dummies2, works in the same way, and create a new join data frame And let's just look at this, the first rows, and it looks like we did a trick. So now let's add these dummy variables to our random forests classifier, using the original columns we have, plus these dummy columns, plus some other that might be useful. Now this is the same code as we had before, but our x variables are just going to be augmented. So we're going to have the list of columns that we created in dummies 1 and dummies 2. And these are just some other arbitrary columns that I found in the parcels dataset. For example, the location. For example, the base year. The number of bedrooms, the number of bathrooms. I don't know if any of these are going to be useful in prediction, but we'll see. And then these lines are exactly the same as we saw before. We're going to create our train test split. We're going to initialize the random forest classifier. We're going to increase to 100 trees. njobs is a parameter that makes use of more cores if you have them on your computer, so it can run a little faster. And now let's initialize and fit the model. So let's see what we did here. It takes a little while to fit, even with lots of cores on my computer. Okay. And we see that we're doing a little better, right? Now we're predicting that just over 0.1% parcels are going to have an ADU, which is much better than before. It was less than 0.1%, I think. But it's still somewhat short of this true fraction. So again, in the next lecture, we're going to look at better ways to assess this predicted performance, but these raw fractions are a useful start. At least we're doing better. So finally in this lecture, let's take a little look more closely at these decision trees. And remember, random forest is an ensemble or a collection of different trees, and we're combining them to get our aggregate predictions. So this previous model we estimated is a little too complex to visualize, so we're going to add a hyperparameter called max depth. And this limits the number of levels of each decision tree. So this is the same as we did before, but we're adding this max depth. So we just have shorter trees that don't have quite as many decision points on them. Now we're going to get 100 estimators, or 100 trees, because we asked for 100 here. And these are going to be stored in this estimators attribute of our RF object that we created. So this is one of the outputs that's created from fitting. So we have 100 of them. Let's just look at the first one. And then we can use the plot tree function in scikit-learn. So we'll plot this tree. What's this tree? Well, this is the one that we stored here. This is just the first one. Then we're going to tell the plot function what our column names are, and we're going to pass it to this axis object that we created here. So we can see that this first decision point is, well, is this use type industrial? And if it's not industrial, then it's going to go to here. So then it's using the store combination, which is some type of use description. Then it's looking at the year built. Then it's looking at the location. And based on these 4 combinations, it's going to give us a prediction. It looks like 163,000 or so end up in this category. So we have lots of these trees. So let's look at the second one, which is slightly different. Here we're starting off with the improvement here. And then we're going, in this tree, we're looking then at the industrial and with use, and then here we're looking at the latitude. And then we're going down into the trees. And here it seems if we have all this combination, we have 20,390 that are false, that don't have an ADU, and 21 parcels that do have an ADU. So we asked Python to generate 100 of these different trees. And you can look at more of them. But while each of them is deterministic, the power of these random forest approaches coming through combining these probabilities. Like each tree, you might look at the decision criteria and think, well, that doesn't make sense. Like, really, this is the best way to produce an ADU, to predict an ADU? And it's not. But combining the probabilities from each of these 100 trees gives us the power of ensemble learning. So the takeaways I'd like to leave you with this lecture are that random forests are one of the most widely used machine learning models, so now you know how to implement it. And we focused here on a binary outcome. Machine learning also works for continuous outcomes. So rather than 0 or 1, ADU or not ADU, we could predict the number of ADUs perhaps. Or we could predict air quality, which is a continuous value. Goes from perhaps an index or the PM2.5 or NOx concentrations. We can also predict data with multiple categories in the same way. For example, mode choice: are you going to take a bus? Are you going to walk? Are you going to drive? Are you going to take an Uber and Lyft? And so on. And so the way that these machine learning models for multiple outcomes or continuous outcomes are going to be set up are going to be really similar. Now you know the syntax for the binary outcome.